ancestors, looking up at the sky must have been an amazing thing. And I know this, because every time I do it, whether it's through a telescope, binoculars, or just my own eyes, I always have a sense of wonder at how amazing, large and beautiful our universe is. Our ancestors, though, looked upon those skies with innocent eyes. They didn't know what those little sparkling dots were, so they made up stories to share around the campfires and used the constellations to find their way in the dark. In Australia, the Kamilaroi nation tell the story of the emu in the sky. Unlike constellations of many nations, the Kamilaroi emu takes up a large proportion of the Milky Way, spanning an enormous proportion of the sky. Over the course of the year, the story of the emu in the sky comes to life. The emu fills the night skies in March, when it is said that the female emu is running, chasing males in the breeding season. During the periods of April and May, when the Milky Way is at its strongest, the emu can be clearly identified. So space and the heavens are a part of our cultural history. Is it any wonder that as we learned more about it, we wanted to go there? Early humans everywhere had a fascination with the night sky, using the signs of the stars, sun, and moon to predict the seasons, thus knowing when to offer sacrifices, plant crops, and start harvests. They built monuments to the heavens, marking out the solstices, the longest and shortest days of the year, and the important stars. Structures like Stonehenge, the pyramids, and the Aztec temples became even more amazing when we recognize the ancient astronomy that went into their construction. The ancient Egyptians, for instance, constructed their year around the heavens. They were fully aware that the year was approximately 365 days long, and divided it into 12 months of 30 days each, as well as 5 ceremonial intercalary days. While this calendar did lose one day every 4 years, what is even more astounding is that they realized that this was the case and developed a secondary calendar based around the star Sirius, which took into account the extra quarter day. Their astronomers also used sundials to tell the time using a variable 24-hour system. This ensured that the day and night were both exactly 12 hours long, regardless of the time of year. At night, they divided the night sky into 36 groups of stars called decans, which could be used to tell the time. Egypt's great buildings were also aligned to the stars. Many temples were aligned to the midwinter sun, letting Egyptians know that they should begin planting soon. The Great Pyramid of Giza is aligned to the cardinal points, and within the Great Pyramid are southern-facing air shafts that point to the star Sirius, with its significance in marking the start of the Egyptian year, and to Orion, associated with death and rebirth, and another recurring theme in Egyptian mythology. In addition, the north-facing air shafts point to the circumpolar stars, which are called the Immortals, because they never set. Early Greek astronomers such as Plato, Eudoxus, and Apollonius borrowed much from their earlier Egyptian and Babylonian counterparts. The name planet comes from the Greek term planetes, meaning wanderer. These ancient astronomers noticed how certain lights moved across the sky differently to the other stars. Plato suggested that the seemingly chaotic wandering motions of the planets could be explained by combinations of uniform circular motions centered on a spherical Earth. His ideas were further developed by Eudoxus, who assigned each planet a set of concentric spheres. By tilting the axes of the spheres and by assigning a different period of revolution, he was able to approximate the celestial appearances. Thus, he was the first to attempt a mathematical description of the motions of the planets. This was of course a geocentric view of the universe, and one that would remain with us until the time of Copernicus and Galileo in the 1500s. Apollonius refined the Greek system with the addition of the eccentric deferent and the epicycle, A deferent is a circle carrying the planet around the Earth. An eccentric one is one that is slightly off-center to the Earth. Epicycles are another small circle carried on the deferent, which carries the planet. These systems together allowed the Greek astronomers to explain retrogradation, which happens when planets appear to reverse their motion through the zodiac for a short time. Modern historians have determined that this model could only have approximated retrogradation crudely for some planets, and not at all for others. Around 140 CE, Ptolemy of Alexandria described a geocentric model of the universe in his book The Almagest that would be accepted as the truth by practically everybody for the next 14 centuries. So the model for our universe had been fixed, with our world taking pride of place in the centre, and this would remain the view of the universe for nearly 1400 years, largely in part because of the religious doctrine of the early Catholic Church. It was now heresy to suggest the world was otherwise, because we were the pinnacle of creation, so of course, we took centre stage. Around 1514, however, the winds of change began. Nicholas Copernicus first showed off his Commentarius, or Little Commentary, a manuscript describing his ideas about the heliocentric hypothesis. It contains 7 basic assumptions. Number 1. There is no one centre of all the celestial circles, or spheres. This meant that objects didn't necessarily all revolve around one thing in the centre, they could actually revolve around other things. Number 2. The centre of the Earth is not the centre of the universe, but only the centre towards which heavy bodies move, and the centre of the lunar sphere. This meant that Copernicus was describing the effects of gravity on people being pulled towards the centre of the Earth, and the lunar sphere, which is the moon, and its circle that it moved on around the Earth. Number 3. All the spheres surround the Sun, as if it were in the middle of them all, and therefore the centre of the universe is near the Sun. Number 4. The ratio of the Earth's distance from the Sun to the height of the firmament, or the outermost sphere that contains all the stars, is so much smaller than the ratio of the Earth's radius to the distance from the Sun that the distance from the Earth to the Sun is imperceptible in comparison to the height of the firmament. By this, Copernicus was saying that the stars were very much further away than all the other celestial bodies they could see in the night sky. Number 5. Whatever motion appears in the firmament arises not from any motion of the firmament itself, but from the Earth's motion. The Earth performs a complete rotation on its fixed poles in a daily motion, while the firmament and its highest heaven abide unchanged. So Copernicus here was the first to describe the Earth as rotating on its axis, and that is the reason why the stars move across the sky. Number 6. What appear to us as motions of the Sun arise not from its motion, but from the motion of the Earth and our sphere, with which we revolve about the Sun like any other planet. The Earth has then more than one motion. Number 7. The apparent retrograde motion and direct motion of the planets arises not from their motion, but from the Earth's. The motion of the Earth alone therefore suffices to explain so many apparent inequalities in the heavens. By this, Copernicus was explaining that the impression of planets moving in the opposite direction to what you would expect was because of the Earth overtaking them in orbits around the Sun. Copernicus decided not to publish his works on the movements of the planets until 1543, just before his death. While many have surmised that this was because of academic and religious backlash to his ideas, it would seem that in Copernicus's case, this was unfounded. In fact, during his own life, Cardinal Nicholas von Schomberg, the Archbishop of Capoue, wrote to Copernicus to urge him to publish his works. Some years ago, word reached me concerning your proficiency, of which everybody constantly spoke. At the time, I began to have a very high regard for you, for I had learned that you had not merely mastered the discoveries of the ancient astronomers uncommonly well, but had also formulated a new cosmology. In it you maintain that the Earth moves, that the Sun occupies the lowest and thus central place in the universe. Therefore, with utmost earnestness, I entreat you, most learned sir, unless I inconvenience you, to communicate this discovery of yours to scholars, and at the earliest possible moment to send me your writings on the sphere of the universe together with your tables, and whatever else you have that is relevant to this subject. Cardinal Nicholas von Schomburg, Archbishop of Capu, to Nicolaus Copernicus, circa 1536. In truth, Copernicus's publication rose barely a stir in religious circles. At the Council of Trent, 1545, just 2 years after his death, neither Copernicus's theory nor the heliocentric model were discussed. In fact, it wasn't until 73 years later, when our next astronomer, Galileo, was to champion the heliocentric model, that the Catholic Church took any official action against it. Galileo Galilei was an Italian scientist who lived from 1564 to 1642. In 1610, he was the first person we know of to use the newly invented telescope to look at the stars and planets. During his nightly observations, he observed small points of light seemingly moving around the planet Jupiter. Galileo realized that these must be celestial objects like our moon, thus showing that Ptolemy's and the Church's idea that there was only one center of orbits in the universe, the Earth, was wrong. Using his new observations as evidence, Galileo argued for the heliocentric model proposed by Copernicus nearly 70 years earlier. He also noticed that the stars looked like little points even when seen through his telescope, and concluded that the stars must be very far away indeed. So not only did he firmly place the Sun at the center of his universe, he showed that the universe was far larger than humans had first believed. Unlike Copernicus before him, Galileo was not so lucky with the Church. He was tried and convicted of heresy in 1633 and was forced to publicly deny the ideas of Copernicus, and was held under house arrest until his death in 1642. Our final astronomer in this episode is Johann Kepler. A contemporary of Galileo, Kepler was a mathematics teacher at a seminary school in Graz, and he later went on to become assistant to astronomer Tycho Brahe in Prague. He invented a very much improved version of the refracting or Keplerian telescope, and like Galileo, studied the planets. In 1610, Kepler received correspondence from Galileo telling him of his discovery of 4 objects orbiting the planet Jupiter. Kepler responded enthusiastically, endorsing Galileo's observations and offering a range of speculations about the meaning and implications of Galileo's discoveries. Kepler then intensified his own studies of the planets and determined 3 laws of planetary motion that firmly put the Sun in the center of the universe, with the planets orbiting it. Kepler's 3 laws of planetary motion can be stated as follows. 1. All planets move about the Sun in elliptical orbits, having the Sun as one of the foci. 2. A radius vector joining any planet to the Sun sweeps out equal areas in equal lengths of time. And 3. The squares of the sidereal periods of revolution of the planets are directly proportional to the cubes of their mean distances from the Sun. Knowledge of these laws, especially the second, the law of areas, proved crucial to Sir Isaac Newton in 1685 when he formulated his famous laws of gravitation. In our next episode, we'll take a closer look at Kepler's laws and how they influenced Newton's laws of gravitation, as well as how Newton's laws and later Einstein's theory of general relativity changed our picture of the universe. Thank you all for watching. and I hope to see you then.